Hello everyone. My name is Vladan Stojnic and I will present the paper Self-Supervised Learning of Remote Sensing Scene Representations using Contrastive Multi-View Coding. This is the joint work with Vladimir Risevich. Self-supervised learning is a method for unsupervised learning of data representations using the supervision signals coming from the raw data. This allows us to reduce the need for massive labeled datasets needed for the training of deep neural networks and to take advantage of all unlabeled data available. This is especially interesting in areas like remote sensing, where we do not have huge labeled datasets like ImageNet, and where transfer learning from ImageNet might be a non-optimal approach, as remote sensing images look quite different from the images in ImageNet, like we show in these pictures. Besides, in remote sensing, a lot of times we have multispectral images available, which further limits the usage of ImageNet pre-trained networks, as they are trained only on RGB images. Currently, most self-supervised methods are trained and tested on images of natural scenes like ImageNet. So, in this work, we evaluate the possibilities of applying self-supervised methods for remote sensing tasks. To accomplish this, we perform self-supervised learning on high-resolution and low-resolution remote sensing images as well as on ImageNet. We also perform self-supervised learning in both RGB and multispectral settings. And for the evaluation of pre-trained networks, we use feature extraction and fine-tuning on downstream tasks of remote sensing scene classification with both high-resolution and low-resolution images. We compare these models pre-trained in a self-supervised manner with networks pre-trained on ImageNet in a supervised fashion. We use contrastive multi-view coding as a method for self-supervised learning, as it is one of the best methods available, and since it is easily applicable to both RGB and multispectral images. This method is based on the idea of splitting the images into two views containing different subsets of image channels. For example, with images in lab color space, one view might contain lightness information and the second view color information. The model then computes representations of these views and tries to pull together representations of views coming from the same image while pushing apart representations of views coming from different images. For the results of feature extraction on RGB images, we can see that self-supervised learning on remote sensing data outperforms supervised with pre-trained networks. It is important to note that remote sensing datasets used for pre-training are about 6 times smaller than the ImageNet. We can also see that the choice of pre-training dataset matters. For the downstream tasks with high-resolution images, pre-training on high-resolution remote sensing images gives the best results, while pre-training on low-resolution remote sensing images gives the results that are worse compared to the pre-training on ImageNet. In the case of low-resolution downstream tasks, pre-training on low-resolution remote sensing images gives the best results, while pre-training on high-resolution remote sensing images gives results comparable to the pre-training on ImageNet. We think this might be due to the inability to learn sharp edge detection filters when we pre-train on low-resolution images. On the other hand, if we pre-train on high-resolution remote sensing images, we can learn both filters for sharp edge detection and filters that would detect features interesting for the special case of remote sensing images. Self-supervised pre-training on multispectral images improves the results by 3 to 4% compared to the pre-training on RGB images only. However, in the case of fine-tuning, supervised pre-training on ImageNet still gives the best results in the RGB setting. But these results can be surpassed or matched using self-supervised pre-training on multispectral images. To conclude, we have shown that self-supervised learning outperforms supervised learning for feature extraction on remote sensing scene classification downstream tasks, even with 6 times fewer images used for pre-training. But in the case of fine-tuning, supervised pre-training still gives better results. We have also shown that the choice of pre-training dataset matters and that you should do self-supervised pre-training on images with similar resolution to the images in a downstream task. Finally, using multispectral images for self-supervised pre-training improves the results and allows us to surpass the fine-tuning results obtained using supervised pre-training.